All right, so rocking through permutations. The way this review is laid out is basically it will have the curriculum outcome, the skill that you'll need to be achieving in the year, and then just example questions underneath, okay? So the curriculum outcome, determine the number of ways to arrange n objects with or without repetition, how to use factorial notation, and the fundamental counting principle. So that's what we're going to review. The first one, determine the number of ways the word laughter can be arranged. Okay, so first of all, we have to ask ourselves, how many letters do we have? 8 letters. Okay, doesn't hurt to just write that down. If I'm using the fundamental counting principle, okay, I would line up 8 spaces. And how many letters do I have to pick from for the first space? 8. And then once I've used one of them, we can't repeat a letter, so there's 7, and then 6, and then 5, 4, 3, 2, 1. The fundamental counting principle, we multiply all these. Okay, and then we'll have our answer from there. Okay, what is the shortcut to using the fundamental counting principle? Factorial notation. Which would be 8 factorial. So in the end, we get a pretty large number, 40,320. Different ways that we can arrange the word laughter. Okay, any questions on that? Pretty straightforward. Okay, one thing to remember with permutations is that order does matter. Okay, and with combinations, order does not matter. When order matters, we can use permutations, and the factorial notation of a permutation is n pick r. Okay, n factorial divided by n minus r factorial. Okay, and n has to be a natural number. Okay. Determine the number of 3-digit permutations of the digits in 12,579. Okay, so first of all you want to look, and there's 5 digits. We need to create a 3-digit number, so we could use the fundamental counting principle. Okay, first I have 5 digits to choose from, then 4, then 3. Okay, so I would get 60 different digits. Okay, or we could solve this using permutations. How many digits do I have at the start? 5, and I need to pick 3 of them. Putting that in factorial notation, it's n factorial, so 5 factorial, over n minus r factorial, 5 minus 3 factorial, gives me 5 factorial over 2 factorial. And again, you get 60. Okay, so 2 different ways that you could solve that. Any questions so far? All right, the next little bit is about permutations when we have repetitions. So whenever we see an object that is repeated, or a letter, or a number, or a vowel, we have to divide by that repetition factorial. Okay, so the notation would be n factorial, okay, fundamental counting principle, divided by the number of repetitions factorial. Okay, so for example, determine the number of 6-letter permutations in the word coffee. Okay, so to start off with, how many letters in coffee? 6 letters. What repeats are we seeing? 2 F's and 2 E's. So to solve this, we would take the number of ways that we could arrange or figure out words using the letters from coffee. Okay, that would be 6 factorial. And we divide by the repeats. 2 factorial times 2 factorial. Okay, in the end, what do you guys get? 180 is correct. Okay, then we moved on to combinations. So combinations are used when order does not matter. Okay, so we looked at examples like committees. We looked at examples like 5-card hand when we're playing poker. There's lots more. For example, determine the number of sets of 3 books that can be chosen from 5 books. So using our combination notation, n choose r, which equals n factorial over n minus r factorial times r factorial. Okay, how would I set this up? What's the total number of books I'm starting with? 5. Out of those 5, I'm going to choose 3. So yes, we could just plug this in our calculator, but just to review the factorial notation, we'd have 5 factorial, which is n factorial, over 5 minus 3 factorial, times 3 factorial, r factorial. Okay, so we get 5 factorial over 2 factorial times 3 factorial. So what, determine the number of sets of 3 books that can be chosen. How many sets? 10 sets. Okay, second example for this one. We're playing from a standard deck of cards. How many cards is that? Good, 52. Who said 54 the other day because of the jokers? Okay, we don't include the jokers, okay? So only 52 cards. Okay, how many ways can a 5-card hand be made if you have at least 1 king? So there's 2 ways we could do this. We could do it using the no restrictions minus no kings at all. Or you could start with 1 king, 4 non-kings, 2 kings, 3 non-kings, 3 kings, 2 non-kings, so on, so on, so on. All of those cases are what kind of cases? If we add or cases, okay? Because it could be 1 king with 4 non-kings or 2 kings, so on, so on, so on. Okay, personally, I think the easiest way to solve this is just by using the no restrictions. Saves a bit of time and work. So we're going to look at no restrictions minus the case if we had no kings. We're taking out the one possibility and leaving the result as all the possibilities of having at least 1 king. So no restrictions. We have 52 cards in a deck. We need to choose 5 of them. Okay, we're going to subtract the possibility of no kings. We have 4 kings in a deck. We have to choose 0 of them. Once we take the 4 kings out of the deck, we have 48 cards left. And of the non-kings, we have to choose 5 of them. So on our calculator, we can use the combination key rather than doing factorial notation. Okay, and we end up with 886,000 and 656. So 886,656. Okay, lots of different hands that you could create. There's a type of question that I haven't put on here, but I think it's worthwhile reviewing. Just remember that n factorial can be broken up into n times n minus 1 times n minus 2, so on, so on, so on, and then 3, 2, 1 so you can break that up, you can expand that. If you're ever asked to solve an equation, just remember that factorial notation can be expanded and you can solve a regular quadratic equation following. Okay. So now we're moving on to the binomial theorem, which we've covered in the last 2 lessons. Okay, so Determine the nth term of the expansion of the binomial x plus y to the power of n. So our goal is to use the general term equation, where n is the exponent of the binomial power, and k minus 1 is the term number. So in this case, we have to find the sixth term of the expansion of x minus 1 to the power of 8. Okay, so our n is 8. If we're looking at the sixth term, what's your k value? It'll be 5, and this should be plus 1, right? Yeah, sorry, can you guys just change that? K plus 1. Okay, so just to be clear, it should be tk plus 1. Alright, so our k is 5. Our x in this case is just x. And our y is negative 1. So if we're asked to find t6, that's actually t5 plus 1. And that will equal 8. Choose k, which is 5. Our x stays as x to the power of n minus k. So 8 minus 5. Our y was a negative 1 to the power of k, which is 5. And then we just have to evaluate. So 8 choose 5. 56. Okay, and then we have x to the power of 3 and negative 1 to an odd exponent ends up being negative. So as a result, we have negative 56 x cubed is our sixth term. Okay, and for number 7, determine the coefficient for the term with x squared y cubed in the expansion of x plus y to the power of 5. So kind of the same setup, but this time we're just finding the coefficient. We don't know the term number, but we do know that we need to have x squared y cubed. Okay, so k is unknown. Our n comes from the exponent on the binomial 5. Our x is just x and our y is just y, so we don't really need to write that down. Using our general term formula, t k plus 1 equals n choose k, x to the power of n minus k, and y to the power of k. Just go ahead, sub in what we know. 5 choose k, x to the power of 5 minus k, and y to the power of k. So looking at the question again, you always want to look back to the question, see if we have any hints that we can stop and just evaluate what does k equal. Okay, determine the coefficient for the term with x squared y cubed. Up to this point, can I make an assumption that k is going to be equal to 3? Yes, because I need y cubed. Okay, so just make a little note here. K is equal to 3 because we need a y cubed. So if k is equal to 3, now we can just start from the beginning. I have t 3 plus 1, which is term 4. And I'll be given 5, choose 3, x to the power of 5 minus 3. That gives me x squared, and I needed x squared, so we did our job. And then y to the power of 3. Alright, what is 5 choose 3? 10, okay. So I have 10 multiplied by x squared, y cubed, and they're asking for the coefficient. So if this was numerical response, my answer would just be 10. So another type of question, sorry I didn't include in the book, is a pathway question. So on the front cover you have a blank space, on the back let's do a pathway question. Yeah. Alright, for this question, I want you to first build a rectangle, 2 boxes south, 4 boxes, 1 to the east.
What kind of a question is this?
Pathways or routes. Okay, and you might just want to put a header on that page, permutations and combinations as well, so you know what unit it's from. So let's start easy. Let's go from A to B. Okay, yes, I could use Pascal's triangle on this, but it's probably easier just to use permutations here. Okay, so going to the east, if I'm trying to go from A to B, there's 4 units east, and I have 2 units south. So to solve this, I would calculate 4 plus 2 is 6, so on top 6 factorial, and you have to divide by your repeats. Okay, repeating 4 east, and repeating 2 south. So the number of possible routes is 15.
Are we gonna be doing
Diagonals? Yeah. Now this is a pretty basic review, and we did just cover that in lesson 7. So keep in mind the rest of the units will be quite thorough, but because we just did cover a lot of the perms and comps, I kept it fairly basic. Okay, but I did think pathways and routes was something that would be worthwhile going over. Okay, so let's draw another shape. Okay, that's question 1. This will be question 2. Okay, again I want you to go 2 south, 4 across. And then we're going to do a bit of an overlap. Okay, going halfway, we're going to go down and build a box like this. Okay, just draw the line all the way across. On the right, just draw 2 more. And then connect all the lines down. And I'll just put 1. Okay, so basically your new box is going to be 3 down and 1, 2, 3, 4, 5 across. Okay, overlapping with the original box. Maybe I'll just take this out. It's gonna help. Okay, so we had our original box, and then there's 2 more below that, and 3 more to the right of that. But we are overlapping. Our goal is to go from A to B. Now, when we have boxes that overlap, can I use the permutations? No. Okay, we have to use Pascal's triangle. Starting with 1 at the top of the triangle, you almost have to tilt your head. Okay, going to the right, it's going to be 1, 1, 1, all the way to that corner. And then going south, 1, 1. With Pascal's triangle, we always add the 2 top numbers to get the number below, creating a triangle. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 1 is 4. 4 plus 1 is 5. 6 plus 4 is 10. Okay, what happens on this corner? What do I do with the 6? Bring it down. Okay, because if I have 6 roots to this corner, it's still going to be 6 roots to here or here. Same thing on this corner up top. If I have 5, okay, going here to here, it's still the same number of roots, 5. Okay, and all along here will be 5, 5, 5, 5, 5. And we can just continue adding the 2 numbers above to get the number below. 6 plus 10 is 16. 10 plus 5 is 15. Okay, 6 plus 16 is 22. 16 plus 15, 31. 15 plus 5, 20. Everyone okay so far? Okay, 22 plus 31 gives me 53. 31 plus 20 gives me 51. 20 plus 5 is 25. 53 plus 51 is 104. Okay, 51 plus 25, we get 76. 25 plus 5, we get 30. Okay, 104 plus 76, 180. Okay, 76 plus 30 is 106. And then lastly, 180 plus 106, we get 286 different roots. Okay, so whenever you have boxes that are overlapping, please make sure you're using Pascal's triangle for that. Okay, now, Abby asked about diagonals. Do we want to do one? I think it'd be useful because it also includes how to solve an equation, so I think it's useful. Okay, this one, I've just memorized the number, it's in your workbook. So, how many sides? To an n-sided polygon that has 65 diagonals. If you want a header for this, this would be diagonals. It'd also be solving equations. Okay, how many sides to an n-sided polygon that has 65 diagonals? So, the formula that you need to memorize is n choose 2 minus n equals the number of diagonals. Now, on your formula sheet, you will be given the formula for combinations. N choose r equals n factorial over n minus r factorial times r factorial. So we're going to apply this formula into the diagonal formula. Okay, but instead of r, we have a 2. Okay, so n factorial over n minus 2 factorial over 2 factorial minus n equals 65. Now I alluded to it earlier. In order to simplify this, we have to expand the n factorial. N factorial can be expanded until we get a factor that can be cancelled out. So n factorial will expand to n times n minus 1 times n minus 2 factorial. And I stop there because I can cancel out the n minus 2 factorials. Excuse me. Okay, so let's go ahead, cancel out those n minus 2 factorials. And I'm left with n times n minus 1 over 2 factorial minus n equals 65. We need to get rid of that denominator, 2 factorial. But 2 factorial is like 2 times 1. Can I just leave that as a 2 instead? Okay, it's just a little easier to look at. Okay, to get rid of the 2 in the denominator, I need to multiply every single numerator by 2. I'm going to multiply this by 2, this by 2, and this by 2. What's going to happen to these 2's? And that was our goal, get rid of the denominator. So expanding, I have n times n minus 1 minus 2 times n, so 2n, equals 2 times 65, so 130. Our goal now is to create a quadratic equation and solve from there. Okay, so n times n is n squared, n times negative 1 is negative n, minus another 2n. Now I'm going to bring that 130 over, so subtract it. That will equal 0. Just combine those middle terms and I get n squared minus 3n minus 130 equals 0. Next step, we're going to factor two numbers that multiply to minus 130 and add to negative 3, negative 13, and positive 10. Okay, now our solutions are n equals 13 and n equals negative 10, which is the extraneous solution. Negative 10. And just to review why, n factorial can only be natural numbers. Okay, so ditch the negative. We have 13 sides to this polygon.